Hi folks, it's Mr. Moodlich here with another video. This time we're looking at lesson number 9. We're really just consolidating and putting everything together, and I'm going to generalize it by introducing these letters for once. So this is actually what, for any given function f of x, these are all the transformations that could be applied to them to give me any kind of distorted a transformed function, right? So I can have the letters a, k, d, and c, and let's go through each one. So A affects me vertically. These are going to be my vertical stretches, compressions, and reflections. When A, the size of A, when it's bigger than 1, I have a vertical stretch, and I say that it's by a factor of A. So essentially my y value gets multiplied by A, every y coordinate. When A is a number between 0 and 1, so it's like a fraction or a decimal between 0 and 1, I say that this is a vertical compression by a factor of A. Whatever A is, I just multiply it by my y's get multiplied by A. If it's a reflection, then, well, it turns out that A would be negative. Whenever the A value is negative, I have a reflection along the x-axis. So that's what that means. So that's all for A, pretty much. Next, we move on to K. So K is going to be just like we saw from previous lesson. Even though we didn't use the letter K, we had numbers there, and it's dealing with horizontal stretches, compressions, and reflections. So it's kind of like the opposite version of A, in that when K is between 0 and 1, I actually have a stretch horizontally, and not only that, but the x value gets multiplied by 1 over K. So literally the K value gets read just like that. It's the number in front of the x, that's my K value. But then when I say by a factor of, I have to use 1 over K. So let's say K was a half, right? Like we could see maybe, okay, well, let's say K is a third. Well, then I would say it's a horizontal stretch by a factor of 1 divided by 1 over 3, 1 divided by K, which is 1 over 3, which would end up being just 3 in this case. So the K value is a third, but the by a factor of is a 3. So essentially, the x's would get multiplied by 3. That's what stretching it does, right? Good. So when K is greater than 1, when the value of K is greater than 1, the size of the magnitude of K, then I say it's a horizontal, K is horizontal, it's a horizontal compression by a factor of 1 over K. So the reason why we have by a factor of in each of these cases for A and K is that this is what we multiply the y or the x by respectively, right? Coordinates to get the new transformed coordinates, mapping rule. We'll see this in a second. And lastly, don't forget when K is negative, it's I got a horizontal reflection, which is a reflection along the y-axis, right? It's like left, right. So it's a reflection across this vertical axis right there. Okay, moving on, we got D right here. So D, again, since it's like the inside of my function, like kind of like dealing with the input here, affecting the input, just like K, D operates opposite to what we believe. So, and there is a negative here as well, as we could see. So if D is like, let's say the value of D is positive, then we're going to move right. If the value of D is negative, we're going to move left. That makes sense, but it's just when it's in here, right? If this was like, let's say x plus 2, well, the D value would be negative 2. So it's the opposite of this. So negative 2 implies that it's moving to the left 2 units. And we could see this in further questions as well. It's one other point I want to mention here for inside the bracket is when we get to questions like this, we always have to factor out and make the coefficient of x 1. So we have to factor it in such a way that it's a 1. So if we have a negative sign here, we have to factor out the negative from both terms inside the square root there. To get this, this will give us the proper D value. So D is actually here, positive 8. So it's shifted 8 units to the right. Okay, and last but not least, the C value. This affects me vertically, vertical translations. I'm moving up or down based on the value of C. So if C is positive, it's greater than 0, then I move up. If C is less than 0, it moves down. C is by far the nicest one out of all of them. Okay, another thing I want to mention is the mapping points. So with these letters now, A, K, D, and C, I need to know that the ones that affect my x are K and D. So it's like inside the input of the function. By a factor of 1 over K means I multiply x by 1 over K, and then I add the D value. Okay, that's the horizontal translation. And in the y direction, I do the scaling first, so a times y, and then plus c at the end. So that's nice. So that's how my mapping rule. X becomes this, any x value, and then y becomes this, any y in the original like parent function or given function. With the transformations, it becomes those respectively. Okay. Another thing that's important to note here is it's okay now to pick just 3 points max from a parent function. So we don't need to pick more. It depends on the parent function. Sometimes we would only need 2. In the case of, like, let's say the reciprocal function, we would need 1. Like the parent function point would be 1, -1, -1, and then 1, 1. Those 2 are sufficient, and then we can kind of freehand the rest. When we have any other function like square root, quadratic, absolute, we want to pick like 3 points and to give us like kind of symmetry or just enough idea. So the starting point, usually that's like the vertex. In the case of like a quadratic, that would be like the vertex right here, and then we get 1 to the left and 1 to the right of that. So we get the full shape. Here, when it's like a square root, we just use 0, 0 as the starting point, and then 1 point after that and another point after that, right? It's kind of like this. Okay, that is in a nutshell everything that you need to know in terms of theory. Now it's just applying this, right? So let's say this is, and these are going to be very repetitive, but the technique here is like we're going to make a table, and this shows all our work here. The first is going to be x and y of the parent function, and then we're going to have the x and y of the transform function with the mapping rules, right? So here I want to rewrite this first with the proper factoring inside, factoring out the negative x. The negative 1 rather, and so I get x minus 8. Now I could pull out the correct a, k, d, and c values. So a is -3, so right here I got -3y plus 7 here, so that's my new y value. That's the mapping, how y gets mapped to the new y. And then for x, it's just negative x, so -1x or just negative x plus 8 right here, because it's the opposite of this, right? So plus 8. And now I just, every x gets negated and then added to 8. So negative 0, 0 plus 8 is this. Negative of 1 is -1 plus 8 is 7, and so on and so forth. And then now I can map these. I can correctly draw these points on here. I can plot them and then connect the dots. There is no arrowhead here because, remember, that was like 0, 0. That was like the parent function started there. That point 0, 0 got mapped to here. So it starts there, and then it goes this way. Right, so just like the square root function starts here and goes this way, that's what happened here. So that's starting point. So it's very good to know the parent function really well. Okay, here we have a reciprocal function. So for stuff like this, the 2 points that we pick are -1, -1, and 1, 1 from the parent function. Those 2 are sufficient. Apply the mapping rules here. So this 1/3 is actually a k value of 1/3, so it's a stretch horizontally by a factor of 3, right? Because it's 1 over k, so that would be 3. So 3x and then -2, because of that positive 2 right there, we flip it, we switch it, we take the opposite, so -2. And then for the y values, it's going to be 4y, that's the a value right there is 4, and then plus 5. So these points get mapped like that. And yeah, so those are it. And the one thing I want you to note for the reciprocal function is to always draw the asymptotes as well. So the asymptotes for my parent function were 0, 0, just 1 over x, right? Y is equal to 0, x is equal to 0, just the x-axis and the y-axis. But now when I have transformations, well, 0, 0, the axes don't get scaled at all, so they stay, but the transformations, the translations do. So it's gonna, that y, the y-axis, x equals 0, is gonna shift 2 units to the left because of this. And the x-axis, so y equals 0, is gonna shift 5 units up. So those are my 2 new asymptotes, which you're required to graph as well. So whenever you have asymptotes, you want to graph them. They're like the fences that my graph never crosses. As long as you plot those 2 points right there, corresponding to this and this, right? The parent function points transformed like that, and then draw the asymptotes and kind of freehand the rest, you will be fine. Okay, moving on. Here, the function is drawn for us. So like this, and I'm trying to apply the transformations to that. So start with the critical points of your function. So this, and this. That's what I've denoted here. And then make sure to rewrite the function with the -2 factored out. So you get x plus 4 inside. And now just apply the mapping rule. So this would be, vertical compression by a half. So, 1/2 y minus 3. The y's are easy. And then with the x, you just got to be extra careful. This would stay negative. That stays. But then the 1 over, so the 2, right here, the k value is -2. So it would be 1 over -2. So, or -1 over 2, same thing. And then I have, that's my x. And then I shift it 4 units to the left, so -4. Okay, if I did the x and y coordinates, if I, if I did the arithmetic here, and I would get these x values and these y values. I can use here decimals or mixed numbers or improper, whatever is convenient for you. In fact, I would heavily, suggest using your calculator here just to make sure you don't make any mistakes. It's very repetitive calculations, right? You're using this correct column. So this would be like -8, right? This would be -1/2 times -8 minus 4, and you should get 0 for that if you did that. Because -1/2 of -8 is +4, 4 minus 4 is 0. So you can see how it's very repetitive. In each case, you're changing x value right here, or to each x. And then the similar for y, right? Except you're using this expression right here. Okay, when we do that, when you plot the points, you'll get this blue line right here. So each dot connects to the previous one, and you get something like this. So this dot, right, -8, -8 became 0, -7. So that became 0, -7, right? So this point went to there. And likewise, this point, -310 became -5/2, so -2.5 and 2. So right here, so it connected like that and like that. Good. Here we have the absolute value function. When I'm looking at something like this, the parent function I know has these 3 points, and then I'm looking at the transformations to this. I will rewrite it with the correct, 2 factored out inside of the bracket. So it looks like this. And then now I can do my mapping points. So the x becomes, well, x is always looking at inside the bracket, inside the function, right? So it looks like a horizontal compression by a factor of a half. So that's why there's x is multiplied by a half. And then I shift 2 units to the left, hence -2. There's a vertical stretch by a factor of 3 and a reflection, hence the -3 there and the y getting multiplied, and a 7 moved up, so +7. So when I take these points and map them using that rule, I get these points. When I take the y's and map them using that rule, I get these points right there. If I graph them, I get this right there. Good. So it's very repetitive that way. It's like I'm saying, it's very much practice-based, so it's good to practice these to develop the speed. But this is the most efficient way of doing it in terms of speed and also just showing all your work as well. Okay, here's a very good one, right? Here I have g of x given to me. So this is g of x given, the sketch right here. I want you to sketch this new function, which is transformations applied to the inverse of g of x. So that means when it's written like this, I need you to find the inverse first. So if this, take 3 points, like literally the 3 critical points on g of x, which is the end points and this turning point right there. So where like the graph actually changes because it's like a line and then it changes to a different line right there. But yes, so take these 3 points. That's what I have right here. And then take the inverse of these because I have to take g inverse and I apply the transformations to g inverse. So take the inverse means swap the x and y's like I've done here. Swap them. I call this new x and new y. That's g inverse x. Okay, good. And now apply the transformations to this. So my x inside like the input right here, it's just negative, so -x stays negative. So change the sign. And in the y, I have a stretch by a factor of 2 and moving 3 up. So it looks like this. And now I just take this set of points, right? Like take this set of x's, apply this rule, means just to change the sign. So -5, -2, 3 becomes -3. And then here, take those set of y's right there and apply this rule. So double the y and add 3. Double of -5 is -10 plus 3 is -7. So on and so forth. And now graph those points right there. And then go in order, go from here to here to here. And then you will get the correct function just like that. So starting from here to here to here. Yeah, that's how you get the correct transformed inverse function. Okay, that was a good one. And then last one here, again, the cubic function. These are the parent function points that you want to pick. 3 points, as you can see. And then you're looking at, well, this is already like I don't need to factor this anymore because the coefficient of x is 1. Then I'm just looking at, well, in the x direction, I'm just moving 4 units to the right, so +4. In the y direction, I'm shifting it, vertically reflecting it, so -y. And then I have +2, that's it. No actual scaling, just reflecting and moving. And then I take these points, these set of points, apply this transformation to get this, take these set of points, apply this transformation, this rule to get this set of points. And I get, when I map that, I get a function, a set of points like that, and I connect them. Again, these 3 points, when I put them, it's not a straight line. Notice that, a cubic looks like this. It looks like this. So this function will also, kind of these points will look like this as well. Okay, and then you can just draw arrowheads to connect them. And that's it. That brings us to the end of that lesson. I'd like you to do this worksheet down here, complete the questions here. So we're looking at combinations of transformations. Read the instructions and follow them here. Graph the base function, the parent function, same thing. List the transformations. So like what's A, what's K, what's D, and what's C. And then looking at applying the transformations to the base function. So sketching what the parent function looks like after it's been sketched. After it's actually sketch it once we know what the transformations are going to be. You have that. This is also, I think numbering here was weird. This should be 6. That should be good. Which reminds me, for a previous question, if you haven't already, we changed this to a +3. It was -3 and it was going to be off the grid, so we made it +3. Just note that correction there. And yeah, so then you have, there you go. You have these other questions down here. So you can sketch this question here and then this one here. And then for this one, it says, for the sake of room, don't draw the parent function. That's okay. Just use your mapping rules to do that. Okay, so that's the homework, this handout. And then from the Nelson Functions 11 textbook, I want you to go to page 70 and complete question number 19, A, B, and C. All right, thank you and have a wonderful day.